In this video, I'm going to be explaining how to use the second derivative test to talk about intervals on a graph that may be concave up or concave down, or points on a graph where we may change concavity. First, let's talk about what concavity is. Concavity is explaining the curvature of a graph. So if we look at this example, we're either curving up or we're curving down, or in other words, we're either concave up or concave down. Sometimes we say we're facing up or facing down. Later on, we're going to use concavity or the second derivative test to determine how a derivative is changing or how the slope on a graph is changing. So is the slope decreasing rapidly or slowly, or is it increasing rapidly or slowly? So we can use concavity in the second derivative test to really explain how the steepness of our slope is changing. But in this video, we'll just focus on concavity. So there are points on a graph where it may change concavity. It may change from facing up or facing down or vice versa. And that specific point is called a point of inflection or an inflection point. We can find those points by finding zeros or undefined values of the second derivative. However, it's important to note that just because we found a zero or an undefined value of the second derivative, that does not ensure that we have a point of inflection. A point of inflection has to be a change in concavity. So we're going to use our test to verify that we actually change concavity, and then we can actually determine whether or not we had an inflection point at a zero or an undefined value of the second derivative. Let's watch this animation to just get a better grasp on concavity. So what we're watching is a tangent line tracing a sine graph. And as it goes, it's changing colors. So when it's blue, it's representing concave up. When it flashes, that's a point of inflection, so it's going to change concavity. And then when it's green, it's representing concave down portions of our graph. So right now we're concave down, and then it flashes right there. That was an inflection point or a change in concavity. Now we're concave up. And then boom, it flashes again, so we changed concavity. Now we're back to concave down. And so essentially that's what we're doing today using our second derivative test, is finding those intervals where we're concave up or down and those points where we may have an inflection point or a change in concavity. So as we evaluate our second derivative using the second derivative test, we're going to either establish positive values on an interval or negative values on an interval. If we get a positive second derivative value, we know that our graph is concave up on that interval. And if we get a negative second derivative value, then we know that our graph is concave down on that interval. So to use the second derivative test, we're going to go through these steps. We're going to find the second derivative. Then we're going to find zeros or undefined values of that second derivative function. And we're going to use those to set up intervals. And then we're going to test values on those intervals to establish whether or not we have positive or negative second derivative values. And that way we'll be able to determine whether our graph is concave up or down. And we'll be able to verify whether or not we had inflection points at those zeros or undefined values. So let's go through an example. Here we're given the function x to the fourth minus 4x cubed. We'll find the first derivative by using our power rule. And then we'll derive that first derivative to get our second derivative. We'll then set the second derivative equal to 0, try and find some zeros or undefined values. Those are possible inflection points. We'll use our test to verify. So by factoring and finding zeros, we get solutions at 0 and 2. We may have changes in concavity happening at those points, so we're going to set up intervals around those points. So we'll set up an interval from negative infinity to 0, then in between 0 and 2, and then from 2 to positive infinity. So we can draw ourselves a little number line with those intervals on it. And then up above, we can state the results of our second derivative test. So I'm going to plug in intervals or plug in values that are on these intervals into my second derivative. So in this first interval, I can plug in a value like -1 and plug it in and just establish whether it's positive or negative. We don't actually have to evaluate it. You can if you feel like it though. If I plug in -1, I have -1 minus 2, that makes a negative value. If I do 12 times -1, I get a negative value. And if I multiply those two together, a negative times a negative is a positive value. So I know that any number that I plug in on this interval is going to give me a positive second derivative result. And I know that my graph will be concave up on that interval. So then I work on my second interval. I need to plug in a number in between 0 and 2, such as 1. So if I plug in 1, I get 1 minus 2, that's a negative value. 12 times 1 is a positive value. And if I multiply those two, I get a positive times a negative, which gives me a negative result. So any number plugged in on this interval is going to result in a negative second derivative. That means my graph is going to be concave down on that interval. Evaluate the last interval. Plug in a value anywhere in between 2 and infinity. 3 would be the easiest choice. If I plug in 3, 3 minus 2 is a positive value, and 12 times 3 is also positive. So a positive times a positive is going to give me a positive second derivative result. So I know that anywhere on that interval, my original graph is going to be concave up. So we can draw conclusions based on this information. I know that my graph, my original function, was concave up on the intervals from negative infinity to 0 and from 2 to infinity. And my graph was concave down on the interval from 0 to 2. And then we can verify our results by graphing the original function and comparing it here. So we said that our graph was concave up on the interval from negative infinity to 0. We could see that in our graph, concave up. At 0, it changed to concave down, so we can verify that at x equals 0, we changed concavity. We do, in fact, have an inflection point at 0. We changed concavity. And then we were concave down from 0 to 2. So about right here is where we're concave down. And then we said that we had an inflection point where we changed concavity at x equals 2. So at x equals 2, we changed concavity. We went from concave down to concave up. And because we had that verification that we changed concavity, we can establish that at x equals 2, we did in fact have an inflection point. And then we remained concave up for the rest of the graph going out towards infinity. So there's how we can use the second derivative test to establish intervals where we have concave up or concave down behavior in our graph. And we can also use it to verify that we have points of inflection or changes in concavity.